Hello there. This is the final summary lecture of the course Transmission Electron Microscopy, Theory of Imaging to Advanced Applications. This has been a course of over 25 odd hours with close to 35 to 40 lectures, where you've seen various modes and principles of operation of transmission electron microscopy. There have been a few demonstration sessions on how the experiments are done. And also, we've seen how the images look like and how do you interpret them. So in this 1.5 hour or 2 hour lecture, what I'd like to do is have a recap of what we've learned in this course, not going into complete details, but highlighting the brief concepts and try to understand what TEM is used for and what are the kind of results that you get from doing such an analysis and how is it useful for not just material science but for applications across various fields. Before I go further into this lecture, I'd first like to acknowledge the contributions of a few people. Primarily, I started learning TEM at TU Delft. I'd like to thank Dr. Chang Su and Franz Tichler, who trained me on the microscope, and of course my PhD supervisor, Professor Henny Zandbergen. Working there has given me immense exposure to try out various things and learn about techniques on TEM. And then I spent some time at Forschungszentrum Jülich. Dr. Govind, he's one of my first PhD students who's in Forschungszentrum Jülich now, and my collaborators, Dr. Amir Tawabi and Professor Rafael Dunan-Borkowski. Collaborating with Jülich has widened my scope and understanding in transmission electron microscopy, and I think anyone who's connected to TEM should actually visit this center because it's an amazing place, and the developments at the forefront of electron microscopy are largely tested in a few labs, and this is one among them. Few others being at the Lawrence Berkeley lab and some of the national labs in the United States. But this is a place where everyone should certainly visit and get an exposure to. Then my student, Mr. Sriharsha, who's been patient with me and helping editing and populating the content for this course. He served as the TA for this course. And the discussions with Dr. Tetsuo Oikawa at GEOL, he's also very friendly and extremely helpful and very knowledgeable in the area of transmission electron microscopy. Discussions with him have always been inspirational, and they give you a simplistic view of quite difficult problems. And of course, the team at IIT Hyderabad and the NPTEL team, I'd first like to acknowledge the support of NPTEL for taking the initiative to organize this course, and Mr. Vijay Bhargav and Mr. Purnachandar from our Center for Continuing Education at IIT Hyderabad, who've played an immense support role in getting the content to this course curated. They've been available round the clock, and their support is something which we really acknowledge. And some important information for those who've done this course and reached this far. I've primarily followed the books shown here, the book by Rolf Erni, and then the text by Tanaka, and of course Williams and Carter, the most famous book on transmission electron microscopy. A few journal articles, especially when I was discussing on aberration correction and high resolution electron microscopy, I followed these classic papers. And also I'd like to mention some of the monographs on advanced reading content from the texts in Progress in Material Science, Progress in Electron Optics. These are quite interesting and elaborate texts which give you a good perspective on how the technique is developed. And of course, some of the technical workshop or resources which are available, Professor Christoph Koch's website, his software that is built for learning TEM simulation, and also the texts and presentations available on CEO's website, which not just give you a perspective on aberration correctors and also their energy filtering systems and so on, but complete microscopy theory in general. And there are a few more web resources which I've indicated here. So let's recap what we've learned in this course. We started with defining what microscope is. The simplest microscope, of course, is a magnifying lens, and then we've drawn parallels between simple stereo microscopes and compound microscopes and transmission electron microscope. So let me show you the image of a stereo microscope here. So this is a simple stereo microscope. So you have an objective lens, you place the object, and when light is incident on the sample, due to the interaction with the sample, which is reflection in this case, you start seeing whatever is visible and the image is formed and you record it over here. So you can see the image here and you can record it on the CCD camera which is on top. If I look at a compound microscope, here is a compound microscope which consists of a condenser lens here, the objective lens here, the condenser lens is on the bottom in this case, and there is a specimen stage. But more importantly, when you are operating this in transmission mode, that is when you are using transparent specimens, and if I turn this upside down, so if the source here is on the bottom, but if I visualize this by turning it upside down and I draw a comparison with electron microscope, the source here is at the top and it is indicated by the number 1. So here you have your electron source, which is typically called as an electron gun, and in this particular microscope you see here, it is actually a lanthanum hexaboride gun or a thermionic emitter, and the objective lens is the heart of the microscope. The objective lens is over here, and the stage here is coinciding with this location here. You have the illumination lenses, and I have indicated the objective lens on the optical microscope on the left. In TEMs, actually you are stacking lenses one on top of the other. So you have the condenser lens, the objective lens, and the illumination lens or projection lenses combined together. But if I draw a parallel, the optical microscope, it is a physical glass lens and the specimen is placed on a stage, and the focusing here is done by moving the specimen up and down physically. Whereas in a transmission electron microscope, you can correct the specimen height physically by moving the specimen holder, which is indicated with the arrow here, through the goniometer here. But the lens here is actually a field lens, and by changing the strength of the lens, you are kind of changing the focus in the transmission electron microscope. And next we have the detection system. You typically use a CCD camera. You can see the image formed on the fluorescent screen here, which is behind this number 4. The fluorescent screen is somewhere here, and then the on axis or off axis recording cameras are below the microscope column. So this is the general layout of the microscope, and then we started understanding each of the components one by one in this kind of a sequence, the way in which they are arranged in a classical upright transmission electron microscope. Now if you look at where the TEM is used for and what do you use TEMs for, you can use TEMs for imaging, for measuring, for modeling, for manipulating matter on all kinds of materials. When I say imaging, the microscopes can be operated in various modes. It is conventional, classical, bright field and dark field imaging, and then you have diffraction, and then you have something else called STEM and high resolution imaging. And with all this, you get the microstructural and morphological information from a specimen. When I say measuring, the crystal structural information, microstructural information, and also whatever compositional information you get by combining with complementary analytical techniques, you get to know the information from the specimen. And by combining the imaging and the measuring and analytical techniques that you use, you build some information on the structure property relationships between a material. So this is where your modeling aspects come in. There is of course something called as crystal structure modeling, and also solving the structure or atomic structure of a material through focus exit wave reconstruction. And there is a lot of modeling done to even model the imaging and the contrast mechanisms in a material as well. So there are various aspects of modeling in connection with TEM. When I talk about manipulating matter through in situ experiments, now you can actually use TEMs as a labs just beyond conventional tools. And there's a lot of real-time experimentation that you can do where you see while the changes are happening in a material, you can record information down to the atomic level. In addition, you can also use transmission electron microscope like a tool where you can form structures and change the physical properties of materials by introducing defects or creating band gaps, and this is also a very interesting area. You can in principle study all kinds of materials provided you prepare the specimen which fits into the microscope, and if it doesn't harm the operation of the microscope vacuum and it is stable under the electron beam. So with all these, if you look at the limitations of the technique, primarily you are limited with the sample size. You are looking at a very small portion of a material. So the typical volume of a conventional 3 mm disc specimen is lower than 0.05 millimeter cube, and assuming the thickness of a specimen here is around 100 to 150 microns. In such a small specimen, the electron transparent region might be even smaller, so the information you get is highly localized. In such a scenario, understanding a material from various complementary techniques and building a bigger picture with bulk characterization techniques is always imperative, and it is important. The next thing is, transmission electron microscopes have the projection limitation problem. That is, after the electron beam interacts with the specimen, whatever is the information that is forward scattered is projected onto the screen or your camera. So what you are actually recording is a two-dimensional amplitude distribution of a three-dimensional specimen. So you are always limited to know where the features that you see are actually located across the thickness of the specimen. There is no depth information. The information is averaged through the thickness. So you need to have complementary tomography kind of techniques which give you three-dimensional information of a material. Then specimen preparation is actually a big challenge. Any material that was shown on the previous slide, you have to prepare it carefully such that you do not lose out the primary information from the material, and it has to be electron transparent. When I say electron transparent, it is really thin. Typically for an inorganic material, it is less than or equal to 100 nanometers across the viewing direction. The common terminology that you should not confuse with is a sample is typically a bulk sample, and when I say specimen, by using suitable preparation techniques, you thin it down such that it is ready for loading in a TEM holder, and the thickness along the viewing direction is certainly within the electron transparent regime. Then you have the problem of radiation damage. It affects largely organics, ceramics, minerals, and in some cases even metallic samples. As an example, the radiation damage increases with accelerating voltage, and quartz is one of the cases where the threshold for beam damage is at around 125 kilovolt. For carbon, it is 86 kilo electron volt, and so on. So you can mitigate the radiation damage by using suitable low dose techniques. There are cryo techniques. You can use fast cameras and sensitive detectors to get information of a material before you lose out the material under the electron beam. If you look at the present trends in electron microscopy, there is a lot happening. Classically, aberration correction has been one of the recent breakthroughs in TEM. By breakthrough, I mean this is already now close to 20 years. I think in 1997, the first successful experimental demonstration of aberration corrected TEM was done, and we crossed the 1 angstrom barrier. So with aberration correction, the resolution is no longer a hurdle. It's more or less become the baseline for advancing the technique of transmission electron microscopy. Here is a table which summarizes the ongoing trends as we discussed today in the year of 2026. There is lots of advancement happening in advanced detection and low dose imaging. We have more faster sensitive detectors which are enabling low dose imaging. There is also ultra fast imaging technique connected to microscope where you are looking at dynamic and beam sensitive samples. There is something I've classified as computational TEM, because once you retrieve the projected potential and the information from a specimen, you can use a lot of phase reconstruction and specimen reconstruction information retrieval techniques such as 4D STEM, tachography and tomography to provide richer multidimensional data. Typically, you are using this for strain and phase. When I say phase here, please don't get confused with the metallurgical phase. It is actually the phase of the electron wave, and phase in turn is related to the electrostatic and magnetic potential from the specimen. You also have three-dimensional analysis, so this helps you overcome the projection limitation in a transmission electron microscope. Then we also have advancements happening in cryogenic and sensitive sample TEM. There are cryo-based methods that are being developed largely for biological materials, but also for a lot of functional materials where you have interesting properties close to the 4 Kelvin or even lower liquid helium temperatures. So there is a lot of advancement happening in this direction as well. Then in situ and operando TEM, you are trying to image the specimen under real-time working conditions. You get dynamic information from the material. This is a field which has been around since the advent of the microscopy, and there have been some in situ studies already explored in the mid 1970s or slightly earlier as well, where people were trying to have some kind of a stimulus onto a specimen and look at how changes happen. This area has got more and more interest, and with the advent of MEMS based devices and by enabling holder based in situ stimuli, the area of in situ microscopy has expanded a lot, and you can see many interesting dynamic processes in materials. Then there is specialized and multimode TEM, like I was mentioning, ultra fast, Lorentz microscopy and spectroscopy integrated TEM capabilities. In fact, there are 5 new state-of-the-art microscopes which are not commercially available being developed at the Ernst Ruska Center, where you are trying to combine more than one technique and integrating it into the TEM. For example, atom probe with TEM is one of the things, and then a high vacuum system with spectroscopy capabilities, an ultra fast microscope, and also a system which is connected to a vacuum system where you can deposit and grow materials on a two-dimensional substrate. So there is a lot happening in this particular area. And like the progress in many fields with the intervention of AI and ML, there is a lot of AI and automation which is used to improve the acquisition and analysis. In fact, some of the commercial microscopes now are already having AI based detection and also orientation tools which are integrated into the microscopes nowadays. And then the most important thing, specimen preparation is extremely important to get good information from TEM. I would say more than 30% or perhaps even more success of a TEM measurement depends on how good the specimen is. There are lots of advancements happening with focused ion beam like the plasma FIB, cryofib, and also transfer methods to enable studying more and more difficult specimens which were not possible quite some time ago. Also, reducing the artifacts while you're preparing specimens becomes an important area. And furthermore, there's a lot of interest with the thriving areas of semiconductor, quantum materials, batteries, catalysis, and soft matter. A lot of work is happening in this area, which is combining more than one of the techniques mentioned above to get meaningful information from a material. So let us look at now the construction of a microscope and recollect some of the concepts that we learned through the course. Here is how the microscope layout looks like, and here is your ray diagram or a schematic of the microscope shown here. There are series of condenser, objective, projection lenses, and you have several deflection coils. Typically these are dipoles, or in some cases you have quadrupoles. By using various configurations within the microscope, you can actually illuminate the specimen in either parallel mode or by forming a probe. and with this there are various techniques with which you get lot of information from a specimen. We'll start by recollecting what we saw with respect to electron sources and why these are important. So when I look at the electron source, it looks like this. The zoomed inset shows you the gun here, which is a thermionic emitter, and typically the electron sources can be classified as either field emission guns or thermionic sources. Within the field emission guns, you also have the Schottky field emitter or you have the cold field emitter. Typically, the source here in a field emission gun is a tungsten needle, whereas in a thermionic source, you have a tungsten filament on top of which you have a lanthanum hexaboride crystal sitting on the top. Now, the difference between a thermionic source and a field emission gun is the construction of a thermionic source is very simple and similar to that of an incandescent bulb. You do not need extremely high vacuum to run a thermionic emitter. So most common, easy to use microscopes for low voltage imaging and all typically rely on thermionic sources, also where you need high throughput imaging. And what happens here is when you start applying a current through a tungsten filament and which has a lanthanum hexaboride crystal sitting on top of it, by overcoming the work function barrier, you are actually allowing electrons to be ejected through the system, and then you have the Veneld grid which focuses the electrons that are diverging to a spot, and this goes through your condenser lens and you form a probe, or you can spread the probe to form a sort of a parallel beam to illuminate the specimen. If I look at a field emission gun, the construction is slightly different because you have an anode, you have actually a double anode, one of which is useful to extract and the other anode also acts to lower the work function barrier, and this helps you with what is called as Schottky field emission. And by lowering the work function barrier, you kind of have emission, and the presence of the dual anode kind of a construction makes you converge the beam to a very sharp spot, and this becomes the source for the condenser lenses which are below the electron source. So with this, you actually have extremely coherent source with a field emission gun. Then if you bring the anode really close to the needle, and you can improve the vacuum even further. So in comparison with the thermionic source, the field emission gun needs to be operated in ultra high vacuum, and if it is even more stable and the anode is brought really close to the fine tungsten needle, you have the emission of electrons by not overcoming the work function barrier but by tunneling through the barrier, and in this case you have the emission happening at low temperatures, and this is called as cold field emission. So I'll give you an example of how a thermionic emitter and a cold field emission looks like. So the video on the left shows you the source, which is a thermionic emitter. When I converge and spread the electron beam by changing intensity on the microscope, you can see that the point of convergence is rather large, and if I compare it with a cold field emitter source, the point of convergence is rather sharp. This gives you an example of how good the coherency is when you compare a thermionic emitter versus a cold field emitter. But there are a few important characteristics of a source which determine the quality of your imaging in a transmission electron microscope, and we'll look at them in the next slide. So if you look at what does the source influence in a microscope, firstly it is the coherency. Within coherency you have two kinds of coherency. One is the temporal coherency and the other one is spatial coherency. By temporal coherence you mean the electrons emitted from the source all have more or less the same voltage. So this means the energy of the electrons is, in practical cases, you would have approximately around 50 eV difference, which in turn changes your wavelength. But by combining with monochromator and also switching to a field emitter, the coherency is significantly improved, and you also have the monochromatic sort of an illumination that is possible. If you look at spatial coherency, what you mean here is all the emitted electrons come from a single sharp point from the source, and a combination of these spatial and temporal coherency significantly affects the resolution of your microscope. In particular, when you are imaging in STEM mode, the spatial coherence plays an important role and temporal coherence plays an important role when you are trying to do analytical TEM analysis. Then we have the stability of the source. There is something called as the source current stability. In thermionic emitters, you can actually switch on the source and then shut down the source after operation, and multiple cycles of this turning on and turning off still doesn't damage your filament or the lanthanum hexaboride crystal. The thermionic emitters are stable but have poor coherence. So we have the Schottky field emitter, which is once switched on, you do not switch on and it keeps running for a period of 1.5 to 2 years or even longer in a few cases if it is maintained well. And to lower the work function barrier, the tungsten needle is typically coated with zirconium oxide, and typically these have a stability of around 1% per hour. But when you look at cold field emitters, on an average, the emission current actually drops by about 5% per hour to even as high as 15% per hour. And what actually happens is, to improve the stability of these cold field emitters, you maintain ultra high vacuum, but when the source current drops below 25% of the anticipated or the expected source current, you do something called as flashing. And in the modern day microscopes, with the feedback control and the digitization of the electronic boards and so on, you can actually do this flashing reasonably quickly, and it is automated, so it makes life easier. In the very old days, thermionic emitters and the Schottky field emission guns were considered more practical and more stable, but nowadays, with the excellent temporal coherency and reasonably good brightness of the cold field emitters, they are used more and more often. Next, we have the brightness, which actually, when I say brightness, it is not how bright some feature looks like. Brightness is actually the flux of electrons that are emitted from the source, and it is measured over a solid angle. Brightness is having a unit of current per area or current per area per solid angle, whereas intensity is once this bright electrons are emitted from the source, when they are incident on the specimen and when they are incident on the screen, it is the intensity that you record on the screen, how bright or how dark it appears, and there is a small difference between brightness and intensity. Brightness is very critical for convergent probe methods, especially in analytical electron microscopy and STEM. So this is what you have with regard to electron sources, and they directly influence the quality of imaging and the resolution of images that you get in a TEM. Moving further, if you look at the electron lenses, almost all lenses used in electron microscopes are sort of round electromagnetic lenses, which are more or less converging lenses. If I understand how the magnetic fields look like and how the construction of a lens looks like, I'll show you this. You have a radial field. Typically, the radial component of the field is reasonably smaller in comparison with the Z component of the field. This is along the direction of the electron beam and the electron microscope. So the source is on the top and the beam traverses in this vertical direction downwards. There are a few manufacturers who use it the other way around, where the source is on the bottom and the detectors are on the top. That is with the neon and the test scan systems. So the radial component of the magnetic field is significantly smaller in comparison with the vertical component, and what this does is, you can actually use what is called as a paraxial ray approximation. So if you look at how the fields are inside an electromagnetic lens, if you can think of the electromagnetic lens analogous to a solenoid, if you think of a current carrying conductor through which current is this way, the magnetic field then is So if the direction is here, the magnetic field is downward, and when a charged particle, that is an electron, enters this kind of a field, it experiences the Lorentz force and it follows a helical path. In some of the older microscopes, you would see the effects of this helical path influencing the image that you record, and you had the image rotation. The newer microscopes, because the electron beam trajectory is reasonably well understood, they compensate for this image rotation, and your image that you record remains stable with various magnifications. So this is how an electron beam moves in an electromagnetic lens. And if I look at the schematic construction of these lenses, typically these are water cooled lenses with a soft ferromagnetic pole piece, typically iron, and the coils are highly conductive pure copper coils which are wound, and when a current goes through this, you are applying a magnetic field along the vertical direction. By lowering the pole piece gap, you are kind of minimizing the aberrations that are caused in these kind of lenses due to the diverging magnetic fields. And the image you see here is a construction. The image on the left, or the schematic on the left, is kind of an immersion lens which was used in conventional high voltage microscopes. If you look at the image, this is from the text from Williams and Carter. The pole pieces look like this, and they are placed in here, and in front of the pole pieces you have sort of a diverging field. So these kind of lenses and the construction and the diverging fields actually cause some distortions, which in turn give you strong astigmatism, which is detrimental to the resolution that you can achieve in electron microscopes. If you look at the modern day microscopes, they typically use something called as a split pole piece kind of a lens. So we have a side entry holder, and when your construction is this way, where the pole piece is separated, initially when we were trying to achieve higher and higher resolutions, more and more immersion kind of lenses were only constructed which used a top entry holder. But nowadays you use a side entry holder with a split pole piece lens, and an example from one of our microscopes is shown you here. This is from one of the side ports of the Geol F200 microscope, and this is how your pole piece looks like for a high resolution pole piece for your objective lens. And the holder, when inserted, comes in somewhere in this gap, and it is not a physical lens but a field lens. And when you have such a field, you naturally have lot of diverging fields, and in turn you have the lens defects. So if I look at what are these lens defects, primarily it is astigmatism. What are lens defects for classic optical lenses? When all your rays that are passing through the lens do not converge to a single point, they form a disk of confusion. In fact, we have looked at this in good detail in our lectures on aberration correction. We will look at it once again when we revisit the summary of aberration correction a little later. But if I think of a sphere that can be fit in this particular region here, or a spheroid, the diameter of this is proportional to the third order of the azimuthal angle here. So are lenses perfect? The answer is no. Especially the electromagnetic lenses are extremely poor in quality when I draw an analog with the optical lenses. For example, when you look at the text in Williams and Carter, they compare the quality of an electromagnetic lens to the bottom of a soda bottle. So if you have a high quality optical lens versus the bottom of a soda bottle, you can see how aberrated this is, and that is how poor in comparison the electromagnetic lenses are. The origin of these defects is of course the diverging fields, and there are various other factors related to the stability of the electromagnetic lenses and the high tension and all the components involved in the electron microscope. Anything that can cause an electromagnetic interference and anything that can cause an instability to any of the electron microscope would actually give you some kind of lens defects. So how can we make them near perfect? This is what we have now, with the advent of aberration correctors, you are trying to minimize the spherical and chromatic aberrations, and also to an order the higher orders of astigmatism as well. And what effects do these defects have? With these kind of lens defects, you would actually deviate far away from the ideally achievable resolution when you are using an electron beam. And because of these many defects, and also having the electron beam closely concentrated along the optic axis of the microscope, and also you have the sort of paraxial ray approximation in transmission electron microscopes, we use largely apertures and diaphragms which kind of cut the higher order deviations of the electron beam to get the best quality beam as close as possible to the optic axis of the microscope. And as a result, you are actually using these kind of apertures which are limiting diaphragms, and they restrict the convergence angle or the collection angle, and they help you improve the quality of imaging. If I look at how the aperture holder typically looks like for a microscope, it is this. You turn the knob here and you insert the aperture of different sizes, and nowadays through these aperture holders you are also putting in MEMS based apertures which are electronically programmable and controlled, and you can use them as face plates to alter the electron beam, and there are different locations where you can place these, and there is a lot that you can do with modifying your imaging system. So if you then look at what we covered on detectors and recording systems, here is an example of one of our microscopes where you see both the fluorescent screen and the recording system, which is a CCD camera. Nowadays you have direct electron detectors, CMOS cameras and so on, and there is a lot of advancement happening in this particular area, and depending on the application and the kind of specimens you study, you configure it with a camera which is useful in obtaining the appropriate dynamic range to record an image. Next, we have seen the construction of the electron microscope now, and if you recollect the specimen preparation techniques, we will recollect what kind of samples have we mentioned that you can study in an electron microscope, and how do we prepare them. Typically, all kinds of materials can be studied provided you prepare them carefully and you ensure that they are electron transparent, and more importantly, they do not affect the microscope when you insert this through a specimen holder in the microscope column. As long as you take the appropriate precautions, only then you can start investigating these kind of specimens. So if you look at the common specimen preparation methods for metallic samples, we have the classical cutting, grinding, polishing, electropolishing and ion milling, and also you can use focused ion beam. The main objective is to prepare thin electron transparent foils, and you can use these for typical microstructure, morphology, phase identification and defect analysis in metallic samples. In ceramics, you can think of mechanical thinning, that is crushing, grinding by a mortar pestle or by a ball mill. And then if I am using bulk ceramic, you have also dimpling, ion milling, FIB, and also dispersing the powder on a simple 3 millimeter grit. So this is also done to achieve electron transparent thin specimens with minimal defects or damage. And most importantly, brittle materials require careful handling. Polymers, these are extremely beam sensitive. There are techniques like ultramicrotome, cryo-ultramicrotome, and also for some you do staining, solvent casting and so on. Polymers and biological specimens have similar specimen preparation methods. The primary intention here is to improve the contrast, and that is why you do staining. For example, people use some silicon oxide beads, and they are used as markers, and you also coat them with gold or something else, and you do some dose tests and so on. In thin films, which are primarily used in the semiconductor area and also in quantum material field now, you intend to prepare cross section or plane view specimens, and then you also prepare them by ion milling or site specific specimens with focused ion beam. The primary intention here is to look at the interfaces and how the defect structure influences the property of the thin film that is deposited or grown. If you think about powders or nanoparticles, you can use classical solvent dispersion, ultrasonication and drop casting and TEM grids. And most importantly, you want to have a good density of the particles on the grid. You don't want it too high nor too low. And more importantly, the medium that you use for suspension should not interfere with the illumination conditions of the microscope. That is, you do not want to have a hydrocarbon layer being deposited on top of the surface. It is extremely simple and widely used methodology for particulate samples. In biological specimen, you typically use fixation, embedding, ultramicrotomy. You use some kind of polymer resins, or in some cases aldehydes or formaldehyde kind of fixation, and then you can section these biological samples, and depending on how you are studying which kind of a material, you can also use cryo ultramicrotome, or there is a methodology called as vitrification, which we briefly touched upon, and these are preliminarily used for conventional imaging or also cryo TEM methods. And then when you look at two-dimensional materials, you either deposit them on a substrate, but you want them to be freestanding, so you want to do some kind of a grid transfer or exfoliation or drop casting. And in some rare cases where the two-dimensional materials are few layers, you also prepare them by focused ion beam as well. The whole intention here is again to preserve the thin structure and minimize the damage as much as possible. You also do not want to have contamination as a consequence of the transfer process. So the most important objective of specimen preparation in TEM is to tailor the material type to ensure electron transparency and also preserve the structure and reliable analysis. In fact, it should be tailor the methodology to prepare the specimen to ensure electron transparency. The thickness requirement is typically less than 100 nanometers and often less than 50 nanometer for high resolution work. For damage mitigation, you also have low dose imaging, cryo preparation, and also dose tests that you need to do for beam sensitive materials. For precision preparation, fib is increasingly used. There is also cryo fib now, where you are also using cryo fib to prepare beam sensitive biological samples also. So that is a snapshot of the specimen preparation methodologies that we saw. And then moving further, there are a host of interesting specimen holders. I briefly touched upon the kinds of holders and some of the applications showing in situ heating and kind of corrosion reactions in a TEM. So typical specimen holders that are compatible with our microscopes here are the single tilt holder, the low background double tilt holder, which is shown here. This is the single tilt and this is the double tilt kind of a holder. And nowadays you can have holders with electrical feed through, and on this you can place a MEMS chip which looks like this. You can design the kind of the circuit you want to have and the kind of signal you want to implement to the sample, and based on the stimulus that you apply, you can modify the specimen, and while this is happening you have electron transparent membranes here, and on top of this you carefully transfer the specimen either by transfer through exfoliation and the other wet deposition routes, or either by focused ion beam transfer or simply by drop casting. Once you successfully transfer the specimen here, you can also do real-time imaging in TEM. So that is about the overview of the broad area of microscopy and the construction of a microscope and how you enable basic holders and specimen preparation and everything and start doing experiments in the microscope. Moving on, we will look at some of the signals generated in TEM, and we will summarize the different imaging modes and the mechanisms that are involved in obtaining these images in the next part of this lecture. So if you look at the signals that are generated in a TEM, a host of signals are generated. Once a high energy electron beam is incident on the specimen, you have secondary electrons, backscattered electrons, Auger electrons, visible light, characteristic X-rays and so on, which are coming out. Broadly, you can classify these as the elastic signal or the inelastic signal. And from the elastic signal, you are largely looking at most of the imaging that is done in the TEM. imaging or diffraction I should say, and from the inelastic signal that is coming, like the characteristic X-rays, the secondary electrons or the Auger electrons. Auger electrons are primarily fixed to SEM, but with the help of characteristic electrons and the inelastically scattered electrons, you can do kind of chemical fingerprinting and also understand the functional properties of a material. So, by using suitable detectors and from the mechanisms that we know related to the interaction phenomenon, depending on the angles of scattering and the physics involved in how the scattering process happens, you can have suitable detectors with which you can detect most of these signals and then get useful information from a material. If I look at the classification of scattering in TEM, I can classify scattering either on the nature of the interaction that is happening, assuming that you have a wave nature. In fact, I always say that you cannot separate the wave or the particulate nature or the dual nature of the electron, but for understanding, you simply look at it as either coherent or incoherent scattering, where the scattered electron wave is either in phase in coherent scattering or there is no direct phase relationship between the incident and the scattered waves. And based on the angle of scattering, you are either looking at the forward scattered or the backward scattered electrons, and 95% or maybe 97% or even higher signal that you obtain in a TEM is forward scattered electrons, and based on this most of our imaging theory is built. Then based on the energy of the scattering event, you can classify it either as elastic scattering or inelastic scattering. Primarily elastic scattering is used in conventional TEM imaging and diffraction, and inelastic scattering you almost use it for all kinds of analytical techniques, and based on the angles of scatter you are placing the appropriate detectors and you are recording the information in a microscope. Let us look at now a summary of what we learnt on imaging and diffraction in TEM, in particular the imaging modes and contrast mechanisms. Now let us draw a parallel with a classical convex lens and understand how a lens functions. If I place an object at the focal plane of the convex lens, the rays that travel through the lens go parallel and they all converge and form some kind of a pattern at the back focal plane. Mathematically, you can relate these through a Fourier transform, and further from the back focal plane, when an image is constructed at the imaging plane, there is another mathematical relation which is the inverse Fourier transform of the information that is recorded at the back focal plane. Now, why is this important? If I take an image as you see on the left here, and if you assume that this is the object, and if it is going through a lens, if I apply a Fourier transform, what I see here in the spatial domain where I can describe the features with x and y kind of coordinates, I can now display them with some kind of a radial coordinates through something called as the frequency and also the intensity here. If you look at it, these portions close to the central spot are called as low frequencies and these are actually called as high frequencies. Typically, you can say that all these are low frequency and the features here are high frequency. And for a lens which has a limited numerical aperture, the frequencies that a lens allows you to pass through at the back focal plane is what decides your lens resolution. And to understand this in more detail, first of all, we should remember that you can link these two through a Fourier transform, and then the image is an inverse Fourier transform of this kind of information at the back focal plane. Let us look at what the classical optics tells us about the propagation of light and diffraction from a point source when you are recording information through a kind of a slit or a double slit or a wide slit or through a circular aperture, and this helps you formulate the concepts of resolution and the formulation of the Rayleigh's criterion. So if you look at the various diffraction cases, if you have a Young's double slit, the key idea is you have two discrete sources, and as a consequence of the superposition of waves that is going through these sources, the outcome is proportional to the phase of the light that is actually scattered through, and you can relate it through some relation, and the information you record appears like a fringe pattern like this. When I have a single wide slit, I can think of it as a slit which is broken down to multiple infinitesimally small sources which propagate forward by the concept of Huygens wavelet and superposition of waves, and the intensity from a wide slit actually appears somewhat like this. If I look at how light propagates through a circular aperture, the wide slit kind of an approximation now, if it is applied to a circular kind of a slit which is wide enough, you do a two-dimensional integration and you get something called as the Bessel's function, and it appears like this. This is called as an airy disk, and if I take a cross section of this, your intensity distribution is a function of the angle of scatter like this, and the first minima is given by this value. And if I have 2 point sources which are overlapping with intensities like this, the separation between either the full width at half maxima or the 80% height or 90% depth of the peak, you can define resolution, and typically for transmission electron microscope the accepted value is around 80% of the peak height, and this simplifies to 0.61 lambda over alpha or sin alpha. So, this is what your resolution is in drawing parallels with classical optics. Now, what you need to remember is in a transmission electron microscope, by switching to electron source instead of light, you are lowering this wavelength here and you are improving the resolution. So, moving on, the kind of information you record in a transmission electron microscope is intensity distribution. If I look at a table like this, here is some kind of ones and zeros, it is kind of a binary information. If I display this two-dimensional array as an image, this checkerboard pattern is what your image appears like. This is called as a bitmap image. Now, in transmission electron microscope, because the electrons naturally are far lower in wavelength than the visible light, there is obviously no color, and what information you record is simply the distribution of the intensity of the electrons that are recorded on a detector. You convert this to an electric signal, and if I display the image that is recorded in terms of a grayscale image, I can think of it as an array which looks like this. Here is a 32 cross 32 array of intensity distribution where the values of intensity range from 0 to 255, and a typical image that is recorded appears like this. Now, the contrast variations you see in a material are typically like this in a transmission electron microscope. So, remember, there is definitely some information regarding the material which you are trying to retrieve and correlate, but the imaging system that is used is displaying only intensity variations which are captured on a fluorescent screen or a CCD camera. And when it is this kind of a process, there can be artifacts which can often be misleading, and before you interpret the intensity variations with some kind of microstructural features, please try to understand why this intensity distribution happens and then correlate it with the knowledge you have on the material. That is when you can do a comprehensive analysis. Now, an important thing is these electrons which pass through the objective lens, they interfere and they form a kind of a spectral pattern at the back focal plane. And if I think of an object which appears like this, and if it is going through an objective lens, what I can do is I can dissociate this kind of a periodic repetitive pattern to sums of sinusoidal waves which appear like this. So what am I trying to achieve here is any image or any periodic pattern, you can break it down to sums of sines and cosines which appear like this. And if I write the amplitude and the phase value of these kind of repetitive patterns, the image which is shown on your left here can be decomposed to sum of 3 repetitive periodic patterns like this. So as you can see, if I take a horizontal cross section across these 3, my phase information is actually changing, which is proportional to what I see here, and the width of these or the frequency of these is changing when I look at the histogram on the x-axis. You can either represent it with a position vector k1 bar, or I can use it as summation of simply one kind of a sinusoidal wave with changing the wave front. So if I look at the mathematical notation of these 3 periodic repeating units, this is how it looks like. And why am I showing this is, any image you record in a transmission electron microscope can be decomposed into these kind of components, and when I take a Fourier transform of this, I can actually switch from the spatial domain here to the frequency domain here. And how does this appear? First, let me take a not periodic kind of an image and let me do a digital fast Fourier transform on this. Your frequencies appear like this, and I introduced you that when I have a lens or an aperture which limits the information at the back focal plane, that is when I am changing the resolution of an image. And if you see, if I use a low pass filter which is allowing only the low frequencies, this sharp edges which are visible reasonably good and these features which are appearing sort of focused will now become more blurred here. This is what your low pass filtering does, and this gives you an idea that your resolution of your imaging system is only as good as the higher order frequencies that your imaging system allows you to pass through. And if I do the opposite now, whereas I apply a high pass filter, the features which are really sharp and detrimental to the resolution of the microscope are all corresponding to the high frequencies. So if I look at the Fourier transform of this kind of a periodic pattern, I would see some bright spot like this, but I would also see reflections at distances like this, and this is proportional to my K1, K2 and K3 which I represented in this particular figure. So this kind of bridges the gap between the periodic patterns that you record in a high resolution image and the diffraction pattern and the diffractogram or the fast Fourier transform you obtain from a periodic repetitive structure that you record in a high resolution TEM micrograph. So this is some of the ideas on what your lens does and how the information is transferred through a microscope. Your microscope can be thought of as a mathematical operator. Your lens actually modulates the phase of the electron wave. Your sample also modulates the electron wave. There is something called as a projected potential, which you will see in the upcoming discussion on high resolution electron microscopy. And the features you record are dependent primarily on the spatial frequencies that your lens allows. Now if you recollect our discussion on electromagnetic lenses, these are highly defective because of the poor field distribution that you have, and as a consequence you are not allowing some of the higher order frequencies, and as a result you are limited in the resolution. Let us now look at the concept of imaging in conventional TEM. Here is an example of a bright field TEM micrograph. The dark features you see here are a secondary phase or a precipitate. The line you see here is a grain boundary, and the feature you see here is actually called as bend contours or diffraction contrast. This is in fact an example of a bent contour, and this is diffraction contrast due to this particular grain being close to the zone axis. What you are representing in this image is the distribution of amplitude over 2 dimensions that you are recording on the fluorescent screen or on your CCD camera. If I try to understand the contrast mechanisms in TEM, we have summarized them with these kind of details. Primarily, you have either the amplitude contrast or the phase contrast. In amplitude contrast, again you have the mass or atomic number contrast, then we had the thickness contrast, you have the diffraction contrast, and then you have the channeling contrast, which is also related to the diffraction contrast. Then you have the phase contrast, which arises from interference between the transmitted and the diffracted beams. This is what lays the foundation for the idea on high resolution imaging, where you are assuming or where you know that the atomic columns are acting as scattering centers, and the lattice fringes that you obtain, which is periodic, is actually kind of an interference pattern. In amplitude contrast, again there is a lot of variation in the material, which is either due to the atomic number difference or the specimen thickness or the diffraction conditions, which generates this amplitude contrast, and I've broken down in detail in this particular slide here. So heavier atoms scatter electrons more stronger. We introduced the concepts of Rutherford scattering experiment, and also defined the scattering cross section, which is defined as the probability of a successful scattering event. The differences in atomic mass and atomic numbers of the constituent elements gives you the atomic number contrast. The same thing in thickness contrast. Thicker regions tend to scatter more than the thinner regions, and this gives you a variation in the intensity of the specimen that you are imaging. And the contrast in case of diffraction contrast depends on how strongly the crystals are oriented or how they are satisfying the Bragg's condition with respect to the incident electron beam. This plays an effect on imaging defects, strain, and variations in the local diffraction conditions. For example, if you want to image dislocations or bend contours or grains and also stacking faults, your diffraction contrast becomes very important, and by using special illumination conditions, you can choose to highlight one of these diffraction spots and image the defects in a very successful way in transmission electron microscopes. Then we have channeling contrast. The channeling contrast in scanning electron microscope is primarily used for ECCI imaging, but in transmission electron microscope you saw this kind of a case where a specimen close to the zone axis. So in this kind of a condition, you want to intentionally orient the specimen to obtain high resolution imaging, but you also, when you look at the larger field of view, the grains that are closer to the zone axis tend to appear darker. This is a consequence of channeling contrast. And then phase contrast, we will look at this in a little more detail when we see the summary of high resolution imaging.